Right now, at this hour, the expansion of space is carrying every distant galaxy away from you at a rate that depends on a single number. We need that number. We have measured it twice, using completely independent methods, with more than 5 sigma of certainty each time. We got 2 different answers. One of those universes contains everything you have ever been told, every distance, every age, every timeline. The other contains something we don't have a name for yet. You are in one of them right now. We genuinely do not know which. Here is how cosmology works. You cannot rewind the universe. You cannot run it in a lab. What you can do is read the light, and if you know the physics, the light tells you everything, where things started, how fast they moved, what the rules were. The Hubble constant, h0, is the single number that describes how fast the universe is expanding at any given moment. Not how fast it was expanding. How fast it is right now, today, while you're watching this. The higher the number, the faster everything is flying apart. The lower the number, the slower. Get h0 right and you get the age of the universe, the geometry of space, and the fate of everything that has ever existed. It is not a minor variable. Team 1 reads h0 from the oldest light in existence, the cosmic microwave. Background. The CMB is the thermal afterglow of the Big Bang, a faint hiss of microwaves that fills every direction of space, left over from 380,000 years after the universe was born. The Planck satellite mapped it with extraordinary precision. They ran it through our standard model of cosmology, the one built from general relativity, quantum field theory, 100 years of physics, and it spits out an answer. 67.4 kilometers per second per megaparsec. Uncertainty, half a kilometer. Team 2 does something completely different. They climb the cosmic distance ladder, a chain of overlapping measurement techniques, each one reaching farther than the last. They start with Cepheid variable stars, stars that pulse in brightness with mathematical regularity, and whose period tells you their true luminosity, which tells you their distance. Then they use those calibrated distances to measure type Ia supernovae, the same brightness every time they explode anywhere in the universe. Reliable as a standard candle across billions of light years. The SH0ES team, led by Adam Rees, Nobel laureate Johns Hopkins, ran that ladder up as far as it would reach. 73.04 kilometers per second per megaparsec. Uncertainty, just over 1 kilometer. Neither team made an obvious mistake. The methods have been audited by people whose careers depend on finding errors. JWST, the most powerful space telescope ever built, was pointed directly at the Cepheids in 2023 and 2024, checking whether the Hubble Space Telescope was distorting the measurements due to crowding in dense star fields. The JWST data came back and said, the Cepheid measurements are off from JWST by 0.02 plus or minus 0.04 magnitudes. Essentially zero. The discrepancy is not a telescope problem. Rees's team calculated that the crowding hypothesis, the last clean escape hatch, can be rejected at 8.2 sigma. That is more confidence than the tension itself. In particle physics, 5 sigma is the discovery threshold. It's the same standard that had to be met before CERN would announce the Higgs Boson existed. A 5 sigma result means that if our model were correct, you'd expect this mismatch to happen by random chance once in a few million attempts. The Hubble tension is at 5 sigma. Both measurements are right. The universe is not. So what could explain this? There are 3 doors. Cosmologists have been walking through them one by one for a decade. Each one looks safer than the last. None of them are. Door 1. Someone made a mistake. This was the comfortable answer. Measurement errors are how science usually resolves things. Someone miscalibrated a detector. Someone's model had a hidden assumption. You find it, fix it, and the numbers converge. But the scrutiny applied to both measurements over the last 10 years is extraordinary. Independent CMB experiments. The Atacama Cosmology Telescope, built separately from Planck by a different team, confirm H0 in the 67 to 68 range. Planck is not wrong. and the distance ladder has been stress-tested from every angle. JWST closed the Cepheid crowding loophole. The anchor calibrators have been swapped out and retested. The statistical survey of 216 H0 measurements published between 2012 and 2022 shows scatter larger than the quoted error bars, meaning the field, if anything, has been underestimating its uncertainties, which would make the tension look smaller than it is, not larger. Kamiankowski and Rees wrote it plainly in their 2023 annual review. Proposed systematic errors are not supported by the breadth of available data. Door 1 is sealed. Door 2. There is something we don't know about. This is the scientifically respectable answer. And it is genuinely unsettling, in a quiet way. The standard model of cosmology, called lambda CDM, contains dark matter and dark energy as ingredients we cannot directly detect. We know they're there because of what they do to everything else. But we don't know what they are. Maybe there is an additional species of particle. A force that only operates at certain energy scales. Something that threads through the early universe without leaving a strong imprint on the CMB. Something that nudges the expansion history just enough to close a 9% gap. The leading candidate is called early dark energy. The idea is that a small fraction of the universe's energy budget, maybe 6 to 10%, briefly behaved like a cosmological constant in the moments before recombination, before decaying away. This would have altered the sound horizon at recombination, the characteristic scale imprinted in the CMB, and when you correct for a smaller sound horizon, the inferred H0 goes up toward 73. Some analyses find that early dark energy brings the tension down to less than 2 sigma. One 2023 analysis found H0 of 70.6 plus or minus 1.4 under an EDE model. Still not perfect, but no longer a crisis. But here's what they don't tell you in the press releases. Every time you add a new ingredient to fix one problem, you break something else. Early dark energy models that raise H0 tend to simultaneously worsen the measurements of how clumpy matter is, a different tension called the sigma 8 problem. You pull one thread, the fabric shifts. The universe is not giving you a clean solution. It is giving you a warning. Door 2 doesn't close. It leads somewhere darker. Door 3. The laws of physics changed. Not the constants tweaked by a fraction of a percent. Not a missing particle that fits neatly into the existing equations. Change. The way the universe expands is governed by the energy content of space itself. If that content underwent a phase transition sometime between the Big Bang and today, if some component of the dark sector literally changed state, the way water turns to ice, then the physics governing the early universe would have been structurally different from the physics governing the one you live in. A 2024 paper in Physical Review D describes a model where a dark sector with its own gauge symmetry, something like a hidden version of the strong nuclear force, underwent a first-order phase transition between Big Bang nucleosynthesis and recombination. The transition released latent heat. It created 2 successive bursts of new radiation species. It modified the expansion history in exactly the window needed to push H0 upward. The model passes current observational tests. We haven't run the next ones yet. And then there is the version of this that some cosmologists discuss quietly, with the kind of care you use when you're not sure you want to be overheard. Some modified dark energy models require that we live inside a region of space, a bubble, where the value of dark energy is locally different from the cosmic average. The inside of the bubble has slightly different expansion dynamics. The outside, the universe beyond the bubble wall, would measure a different H0. We would never know the bubble existed unless we could see its boundary. And in these models, the boundary is not static. It is expanding, outward from where we are, at the speed of light. You will never see it coming. There will be no warning, no precursor signal, no flash. The boundary of a changed physics region propagating at the speed of light is, by definition, traveling exactly as fast as any information about its existence could reach you. If this model is correct, the different universe, the one with different rules, is already here. Right now, parts of space outside our observable horizon are operating under physics you do not have equations for. And the only reason you don't know this is that the light carrying that information hasn't arrived yet. Here is the part no one writes about. The atoms in your body are not from this universe. Not in the sense that the universe changed dramatically since they formed, though it did. In the more specific sense, every carbon atom in your cells, every oxygen atom in your blood, every iron atom in your hemoglobin was forged in stellar cores that burned and exploded billions of years before the sun existed. Those stars lived their entire lives, birth, fusion, collapse, death, inside a universe where the expansion rate, the sound horizon, the ratio of matter to radiation, were all tuned to values that no longer exist. They are artifacts. The early universe's first 20 minutes decided everything that would become chemistry. The ratio of hydrogen to helium, 75 to 25 by mass, was locked in while the universe was still too hot to form a single atom. That ratio determined which stars could exist, which stellar deaths would happen, which elements would be scattered into the interstellar medium. If those first 20 minutes had different physics, different expansion rate, different energy content, you do not get different atoms. You get no atoms. Or you get atoms no chemistry can use. The universe that made you is gone. What's left is running at different numbers, and we can't agree on which ones. Licia Verde, one of the architects of modern precision cosmology, put it this way: when I was a PhD student, knowing the Hubble constant at the 40 to 50% level was great. Now, we are declaring a crisis in cosmology because there is a discrepancy at the very few percent level. We built the most precise instruments in human history. We mapped the oldest light in the universe. We built a cosmic distance ladder that reaches 400 million light-years. We got our uncertainty down to 1 kilometer per second per megaparsec. We sharpened the knife until it could cut individual photons. And what we found is a crack, not a rounding error. A structural crack in the foundation of the model that explains everything. David Gross, Nobel laureate, said it at a workshop in 2019. Not a tension, not a problem, a crisis. Adam Rees said it differently. This may be the most exciting development in cosmology in decades. Both of them are right. And the fact that both of them can be right about the same thing is itself the most unsettling part of this story. There is no answer at the end of this video. That's not humility. That's the actual state of cosmology in 2025. Both measurements are right. The gap is 5 sigma. JWST didn't close it. The leading theoretical fix makes something else worse. And the most exotic explanation, that we live inside a region where the physics is locally modified and the boundary is propagating outward at light speed, cannot be ruled out by any data currently available. The people who built the instruments that created this crisis are still working. The James Webb Space Telescope is still running. The next generation of CMB experiments is under construction. The Dark Energy Spectroscopic Instrument is cataloging millions of galaxies to map the expansion history in higher resolution than anyone has attempted. They will get a better answer. Or they will get a stranger one. Here is the question that will follow you. If the laws of physics were different in the early universe, if the rules that built you are not the rules you're living under now, then the constants in your physics textbooks, the ones you've never thought to question, are not the laws of physics. They are the laws of this physics, and you have no way of knowing how many there have been.